All right, let's dive right in. Today, we're talking about one of the most important concepts in all of computer science, data structures. You can think of them as the secret ingredient, the invisible framework behind pretty much every piece of software you've ever used. So let's pull back the curtain and see how it all really works. You ever stop and think about how an app like TikTok or Instagram can just, instantly find your friend's profile out of literally hundreds of millions of users? Or how Google can search the entire internet in less than a second? Well, that's not magic. It's just incredibly smart data organization. And that is what this is all about.
So, here's what we're going to cover. We'll start with the basics, what a data structure even is. Then we'll get into the two main families. After that, we'll see a really cool practical example with polynomials, check out some advanced tools, and then wrap it all up with why this stuff is just so critical to understand.
Okay, so let's start at square one. What exactly are we talking about when we say the words data structure?
Think of it this way. You could just throw all your clothes into one giant pile on your bedroom floor. I mean, technically it's all there, but good luck finding a matching pair of socks, right? That's data without a structure. A data structure is like using a dresser. You've got drawers for shirts, for pants, for socks. It's a specific format for organizing and storing your data so you can actually use it efficiently.
And this isn't just some abstract theory I'm talking about. In fact, if we look right here at these university course notes, we can see the exact definition that real software engineers learn. This is the bedrock, and it all starts with this simple, powerful idea, handwritten right on the page.
Okay, so not all dressers are built the same, right? Data structures are usually split into two big families, and it all depends on how they arrange the information inside them.
On one side, you have linear structures. This is pretty straightforward. Think of it like a train, where each car is connected to the one before it and the one after it in a straight line. Simple, sequential. On the other side, you've got nonlinear structures. This is more like a family tree. You've got branches and connections going off in all sorts of different directions.
So for linear structures, you've got things you've probably heard of, like arrays, stacks, and linked lists. They're all basically different kinds of lists. For nonlinear, the big ones are graphs, which kind of look like a web or a network, and trees, which have that classic root and branch shape. For today, we're going to focus mostly on that linear family, just to see how powerful even these simple sequential structures can be.
Okay, theory is great and all, but let's see how one of these linear structures, a linked list, can solve a real problem.
So here's the challenge. Let's say we want a computer program to understand algebra. How in the world would it store an expression like this one? It's got different parts, coefficients, exponents. You can't just type it in as a sentence and expect the computer to get it. You need to give it some structure.
And this is where a linked list is perfect. First, we take the 4x cubed part and stick it inside a little container. We call it a node. This node holds its two important pieces of info, the coefficient, which is 4, and the exponent, which is 3. Then, we do the exact same thing for the second term, 2x1. And finally, this is the key. We create a pointer that links the first node to the second one, creating a chain. And just like that, we've perfectly represented the whole expression in a way a computer can understand.
And what's so cool is seeing how this idea translates directly into actual code. If you look at this C++ example, each of those nodes we talked about becomes something called a term object. And you can see it right there. It has a place for the coefficient, a place for the exponent, and, crucially, a pointer called next that points to the next term in our chain. It's a perfect one-to-one mapping of our idea.
Now, once you have these basic list-based structures down, you can start to build some incredibly powerful tools on top of them. So let's look at a couple of more advanced examples.
First up is something called Radix sort. Now this one's a little bit of a mind bender. Most sorting algorithms work by comparing two numbers. Is 5 bigger than 3? Radix sort doesn't do that at all. Instead, it sorts numbers digit by digit, starting from the rightmost digit, the ones place, and working its way to the left. Let's just see it in action. It'll make more sense. Here's our messy, completely unsorted list of numbers. We've got 170, 45, 75, they're all over the place. The goal is to get these into ascending order, smallest to largest. Okay, first pass. We only look at the very last digit of each number, the units place. So 170 gets grouped with the numbers ending in 0. 802 and 2 are put together because they both end in 2. We reorder the entire list based only on that single rightmost digit, completely ignoring everything else for now.
Next up, we do the exact same thing but for the tens place, the second digit from the right. We take our newly ordered list and resort it again.
Numbers like 802 and 2, which have a 0 in the tens place, move toward the front. Numbers like 170 and 75 move back because their tens digits are 7. We're just resorting the whole thing using only that second digit. And you can probably guess the final pass. We sort by the hundreds place. The numbers that don't have a hundreds digit, like 2 or 24 or 45, are treated like they have a 0, so they stay at the front. The others just fall into place. And after that last pass, look at that, a perfectly sorted list. And the craziest part, we did it without ever directly comparing one number to another.
Okay, next up is a really fascinating variation called a multilist. So remember how our polynomial node had one pointer called next? Well, imagine a node that has 2 or 3 or even more pointers. Each one of those pointers makes it part of a different list all at the same time.
So, why on earth would you need something that complex? Well, it's used for some really powerful stuff. Think about a university's course registration system. A single student node could be part of the Chemistry 101 list and the Calculus 2 list at the exact same time. Oh, and notice that first bullet point, graph representation? This is where things get really cool, where linear structures actually become powerful enough to build their nonlinear cousins. But here's the crucial thing to understand. It's a trade-off. The huge advantage is that you save a ton of memory. You don't need to copy all of a student's data for every single class they take. But the downside? It's way more complex. These things are a lot harder to build, manage, and fix when they break compared to a simple list.
Which brings us right to our final takeaway. After looking at all these examples, from a simple list to a complex multi-list, what's the big idea we should walk away with?
It's this. Choosing the right structure for your data is everything. It is the difference between an app that feels lightning fast and one that just lags and crashes. It's the difference between a search that takes a millisecond and one that takes a minute. Data structures truly are the silent, invisible architects of the entire digital world we live in.
We've seen how a simple idea like a linked list can represent complex math, and how a really clever sorting trick can create order out of chaos. These aren't just academic puzzles. They are the literal, fundamental building blocks of all software. So now that you understand a little bit more about them, the only question left is, what will you build with